Look down at the floor right now. It feels solid, doesn't it? Unmoving. Permanent. But what if I told you that every map you have ever trusted is nothing more than a temporary snapshot of a face that refuses to hold still? Right now, the ground beneath you is drifting. Quietly. Relentlessly. But here is the massive, planetary-scale mystery that keeps geologists awake at night. If Earth can do this, why can't Venus? We have two worlds. They are nearly identical in size. They are made of the exact same rock. They were born in the exact same solar nebula. Yet one becomes a living, breathing, moving mosaic of continents, and the other locks itself into a blistering, rigid, dead mask. Tonight, we are going to audit the planet beneath your feet. And by the end of this video, you will never look at a map, an ocean, or a simple drop of water the same way again. It is late. You are sitting in a dim study. The only light comes from a small desk lamp that turns scattered papers into islands of gold. Outside the window, rain taps the glass with the steady patience of a metronome. Tick. 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 It feels like time itself is taking measurements. Spread across your desk are maps and fragments of evidence. You have coastlines traced in thick black ink. You have fossil catalogs filled with unpronounceable Latin names. You have earthquake records that look like scattered confetti. And you have cross-sections of the deep seafloor that resemble the ribs of some ancient, buried beast. Your finger lands on the westward bulge of Africa. Then, your hand drifts over to the eastward curve of South America. You slide them together. They fit. They fit way too perfectly. Suddenly, the temperature in the room seems to drop. Not because the air actually moved, but because your entire mental model of reality just shifted. If continents can move, then the word stable is a complete illusion. Borders are temporary. Giant mountain ranges are just geological arguments still being negotiated. Oceans are not permanent fixtures, they are just passing phases. Even the chair you are sitting on is participating in a slow, violent choreography that you were never taught to see. So here is the fundamental human question we are really asking today: what kind of world do we actually live on? One with a fixed, frozen face, or one that continually remakes itself, destroying and rebuilding its own skin? And the sharper, almost unfair follow-up question: why does Earth get to be that kind of dynamic world, while Venus, a planet so similar you could practically call it our twin sibling, does not? Welcome to the Science Audit. Our claim on the table today is highly specific. Earth operates on a system of global plate tectonics. We are not just talking about continents drifting in some vague, magical way. We are talking about a full-blown planetary operating system. Mobile plates. Creation zones where brand new crust is born. And destruction zones where old crust is swallowed back into the fiery interior of the planet. For this audit to pass, the evidence has to do three distinct things. First, it has to show measurable motion. Something you can track with hard data, not just imagine. Second, it has to show global recycling. A closed loop of birth and death, ridge and trench. Third, it has to point to a physical mechanism that can actually run for billions of years without resorting to magical thinking. And then, when Earth passes that test, we are going to ask the deeper, much darker mystery. If other rocky worlds also have hot interiors, if they also have the basic internal, stirring, that should move things around, why don't they all look like Earth? Why isn't plate tectonics the default setting of the universe? Let's travel back to a moment when that question didn't even have the vocabulary to be asked. It is the year 1912. You are sitting in a crowded European lecture hall. It smells faintly of damp wool coats and heavy chalk dust. People are shifting in their seats the way they always do when something highly uncomfortable is approaching. It feels like a cold draft creeping under a door. At the front of the room stands Alfred Wegener. He is speaking, and you can literally feel the academic establishment bracing itself to tear him apart. You see, Wegener isn't a geologist by training. He is a meteorologist. He is an outsider with the wrong background, standing in the wrong temple, preaching to the wrong priests. But he has something in his hands that the room simply cannot ignore, an undeniable pattern. He points to the margins of the Atlantic Ocean, Africa and South America. The puzzle piece fit is suggestive, sure. People had noticed that for centuries. But Wegener doesn't stop there. He pulls out fossil records. He shows the exact same ancient species, like the freshwater reptile Mesosaurus, or the heavy-seeded Glossopteris fern, turning up on continents that are now separated by thousands of miles of deadly saltwater. These animals couldn't swim across an ocean. The seeds couldn't blow across it. He keeps going. He shows massive geological formations. Ancient mountain belts in North America that perfectly align with mountain belts in Scotland if you just slide the continents back together, like taping a torn photograph. He shows mind-bending climate clues. Glacial scratches in the bedrock of hot, tropical places like India and Africa. Scratches that make absolutely zero sense unless those land masses were once sitting right near the South Pole. You feel it in your ribs. That low, rising sensation when a dangerous new idea starts to suck all the oxygen away from the old, comfortable story. But then, almost on cue, the pushback arrives. And it is brutal. What is the engine? A famous professor demands from the back row. What literal physical force could possibly move entire continents through solid rock? Another voice chimes in, dripping with sarcasm. Continents are way too rigid. The seafloor is way too strong. You are asking us to believe that continents are out there plowing through ocean crusts like wooden ships breaking through thick ice. It's physically impossible. And that was the fatal problem. Wegener had an incredible map of the crime scene. He had the motive. He had the bodies. But he did not have the murder weapon. He could not explain the how. Wegener would eventually die on an expedition in the freezing, brutal conditions of Greenland in 1930, never knowing that the entire world would one day admit he was right. If you have ever been absolutely certain about a pattern, but you just couldn't explain the mechanism. If you've ever felt that agonizing frustration where the truth is right in your hands but not yet in your language, you know exactly what that room felt like for him. So we linger there for a moment. Because this is the first doorway of our audit. The world might be mobile. But to make mobility a scientific reality, you need something much heavier than resemblance. You need a functioning system. Now we jump forward. It is the mid-20th century. World War II has just ended, and it left behind a powerful new technology. You are no longer in a dusty lecture hall. You are standing on the deck of a massive research vessel. The steel deck vibrates violently under your boots as the ship cuts through dark, freezing ocean water. The horizon is just a blunt, gray line. The air tastes heavily of salt and diesel exhaust. Far below you, in the pitch-black crushing depths, an instrument is doing something quietly revolutionary. It is listening. Sonar is sending sharp acoustic pulses down into the abyss, and recording their echoes to measure depth. Back in the labs, a brilliant cartographer named Marie Tharp is taking these thousands of sounding records and plotting them on paper. And as she draws, the ocean floor begins to reveal itself in jagged, terrifying strokes. What it reveals is not a flat, smooth, boring basin like a giant cereal bowl. That is what everyone expected. Instead, it is a mountain range. An underwater, global, continuously linked mountain range that threads through all the oceans of the world like a stitch seam on a baseball. The mid-ocean ridges. The longest mountain chain in the solar system, and it is entirely underwater. You stare at the data as if the paper might suddenly blink. Why is there a massive mountain chain down there? Why is the seafloor elevated along a jagged line that snakes completely around the planet? And then, other bizarre measurements start to stack up like hard evidence on a detective's desk. Heat flow. The ridge isn't just topography. It is physical warmth. The seafloor is measurably hotter right at the ridge. The rock itself is younger there. In fact, and this is the part that lands like a lead weight in your hand, the seafloor is systematically incredibly young right at the center of the ridge, and it gets systematically, predictably older the further you move away in either direction. That pattern is not just decorative. That pattern is a clock. Think about what this implies. If the crust is youngest at the ridge, then something violent is happening there. Something like creation. The ocean floor isn't some ancient, static relic from the dawn of time. It is being made. Right now. Continuously. Hot magma is rising up at these ridges, freezing into new rock, and then being pushed outward like a massive, planetary-scale conveyor belt. But wait. If you are constantly making new seafloor, you run into a massive physics problem. Conservation of mass. The surface area of the Earth is not expanding. We aren't blowing up like a giant balloon. So, if millions of tons of new rock are being pushed out every single year, where exactly does the old seafloor go? Hold on to that question. It is about to become the hinge of everything we know. Because now, we are moving out of the ocean and into a highly sterile laboratory. Imagine the hum of warmed electronics. A scientist is placing a sample of basaltic rock into a magnetometer. They check a reading. Then another. At first, the numbers don't look poetic. They look like pure, chaotic noise. But then, slowly, the noise begins to resolve into something eerily, beautifully symmetrical. Magnetic stripes. I want you to imagine the seafloor as a giant, incredibly slow-moving tape recording. When molten rock emerges at a mid-ocean ridge, it contains tiny magnetic minerals. As the rock cools and hardens in the freezing ocean water, those tiny minerals lock into place, pointing directly toward the magnetic North Pole. They freeze like tiny compass needles trapped in stone. But here is the wild part. Earth's magnetic field has a strange, violent habit. It flips. North becomes south. South becomes north. It doesn't happen on a human schedule. It isn't entirely predictable. But it happens often enough over millions of years to leave a deeply layered history. So, if the seafloor is actually spreading outward from the ridge, and if Earth's magnetic field is reversing over time, then the ocean floor should carry a literal barcode. Massive stripes of normal and reverse magnetic polarity, perfectly mirrored on both sides of the ridge. Exactly symmetric. Like a vinyl record duplicated in heavy stone. And that is exactly, perfectly what the data shows. In that single, breathtaking moment, you don't just have a nice idea anymore. You have a written confession provided by physics itself. The Vine-Matthews-Morley hypothesis becomes undeniable reality. The seafloor is actively spreading. The mid-ocean ridge is a factory. The planet is literally manufacturing its own crust. But remember our massive problem? We are still missing the other half of the loop. We found the factory. Now we need to find the graveyard. The place where old crust dies. So let's turn the lights down again and look at a very different kind of map. You are standing over a world map, but this one is covered in thousands of tiny glowing dots. Every single dot represents an earthquake. A sudden, violent release of stress. A snap in the planet's skin. At first glance, it looks like pure chaos. Just a shotgun blast of data. But then you take 3 steps back, and the dots begin to connect into massive arcs and lines, like terrifying constellations. Welcome to the Ring of Fire. The edges of the Pacific Ocean. Long, sweeping scars that wrap completely around the world. Here is the deeply unsettling part. Some of these earthquakes don't stay near the surface. They occur incredibly deep. 200, 300, even 600 kilometers down into the earth. According to the laws of physics, that absolutely should not happen. Rock at that depth is so hot, and under so much pressure that it behaves like warm, highly viscous putty. Deep rock should stretch and flow. It should not snap and cause an earthquake. You can't snap warm putty. Yet the seismic data insists, screaming at us, there is brittle, violent failure happening deep inside the Earth's mantle. Now you plot those exact deep earthquakes on a 3D cross-section. And suddenly you see it. The ghost in the machine. A heavily slanted plane of earthquakes descending deeply into the mantle at an angle, looking exactly like a giant sword being slowly, violently pushed into a sheath. These are called Waradi-Benioff zones, named for the brilliant scientists who first recognized the pattern. And they are the exact fingerprints of a massive slab of cold, rigid, heavy oceanic lithosphere sinking down into the hot interior of the planet. This is the missing sink. The graveyard. The place where oceanic crust is brutally destroyed. Subduction. And just like that, the loop perfectly closes. Ridges create new crust. Subduction zones consume old crust. And transform faults. Those massive sideways tears in the earth, like the famous San Andreas Fault in California, stitch the geometry together so the rigid plates can slide past each other without ripping the entire surface of the planet to shreds. At this exact point in the audit, you might physically feel the shift in your brain from, maybe this is true, to, oh my god, it's real! Because plate tectonics is no longer just a poetic metaphor for drifting land. It is a precise engineering diagram of a working machine. But we are not done. Now we must audit the motor itself. because finding evidence of motion without explaining the motor is like finding a running car and assuming it moves by magic. Earth's incredible engine begins with one thing: heat. Some of this heat is primordial. It is the leftover thermal energy from the violent, chaotic formation of the planet 4.5 billion years ago. From the endless asteroid impacts. From the intense friction of heavy elements like iron sinking to form the core, and lighter elements rising to the surface. But a massive amount of the heat is radiogenic. It is the literal heat released by the slow, constant radioactive decay of isotopes deep in the rock. Uranium, thorium, potassium. This incredible heat doesn't turn the mantle into a sloshing liquid ocean of magma. That is a common myth. Instead, it makes the mantle something much stranger, a solid rock that can actually flow. Here is the metaphor to lock into your brain. Think of the Earth's mantle like extremely cold, thick honey in a jar. If you tap the jar with a spoon, the honey feels rock hard. It acts like a solid. But if you apply a steady pressure to that honey and give it time, hours, days, it creeps. It flows. It deforms. The solid rock of the mantle does exactly the same thing. It convects. Not in minutes. Not in human years. But over tens of millions of years. Convection is simply heat trying desperately to solve a problem. Hot material deep near the core becomes buoyant, so it slowly rises. When it gets near the surface, it cools down, becomes incredibly dense, and slowly sinks back down. It is the exact same process that happens in a lava lamp, in a boiling pot of thick soup, or in the storm clouds of our atmosphere. Inside the Earth, the scales are monstrous, but the speeds are humiliatingly slow. We are talking centimeters per year. Literally the exact speed that your fingernails grow. But over the vast, unimaginable abyss of geologic time, fingernail growth can push continents entirely across oceans. Now, add the structural architecture to this engine. The outermost shell of our planet is called the lithosphere. This is the crust plus the very uppermost, coldest, hardest part of the mantle. It is highly rigid. It is brittle. Underneath that rigid shell is the asthenosphere. It is warmer, weaker, and much more capable of deforming. It is not a liquid ocean of magma, but it is a zone where the rock's overall strength drops just enough to let the rigid lithosphere above it glide. So, let's clear up a massive misconception right now. Plates are not just continents sliding around. Plates are massive, broken slabs of the lithosphere. They are made of both heavy oceanic rock and lighter continental rock, welded together into a single moving unit. Continents are just the thick, buoyant passengers riding on top of some of these plates, floating like thick cork rafts embedded in denser, thinner oceanic lithosphere. And this massive global system operates perfectly on three essential types of boundaries. Divergent boundaries. This is where plates pull apart, like at the mid-ocean ridges. Magma rises to heal the wound, freezing into brand new oceanic crust. Convergent boundaries. This is the violent collision. Subduction zones. Where dense, heavy, old oceanic lithosphere bends deeply and sinks back into the mantle, recycling material and triggering explosive, terrifying volcanic arcs at the surface. Transform boundaries. This is where plates grind sideways past each other, relieving geometric stress, transferring motion like the heavy steel joints in a factory machine. That is the mechanism. Heat drives convection. Convection and immense gravity drive the plate motions. Ridges and trenches maintain the exact surface area of the globe. It is a 100% efficient, self-sustaining, global recycling plant. And here is the modern reality check that makes this almost absurdly, undeniably concrete. Today, we don't need to guess. We have satellites in space. We can physically measure plate motion right now, using GPS down to the millimeter per year. The solid ground you are sitting on is actively drifting as you listen to my voice. Your city has a measurable velocity vector. Your entire continent is migrating. I do not mean metaphorically. I mean literally, physically moving. So, the audit of our first question. Does Earth actually have plate tectonics? Passes with a kind of overwhelming, slam-dunk clarity. Which means we are now finally allowed to open the terrifying door that has been waiting behind the curtain this entire time. If convection is so common, if absolutely any rocky planet that has a hot interior should naturally convect, why isn't plate tectonics common? Why isn't Earth normal? Why are we the weird ones? This is where the story gets incredibly sharp. Because the intuitive, obvious idea, heat makes motion, therefore plates should always move, turns out to be radically incomplete. Let's put this idea through its first extreme stress test. Convection alone is simply not enough. A rocky planet can have a fully convecting, churning mantle deep inside, and still have a single, thick, unbroken outer shell that never moves. Think of a thick pot of hot stew sitting on a stove. The stew is rapidly circulating underneath, bubbling and moving, but there is a thick, solid crusty skin that has formed on the top. The skin stays perfectly intact while everything boils below it. Planetary scientists call this terrifying scenario a stagnant lid. It is a dead world where the lithosphere is just one giant, continuous shell. There is no global network of broken plates. There is no recycling. So the fundamental question of planetary survival becomes, what actually breaks the lid? And more importantly, what keeps it broken? Because cracking an eggshell once is incredibly easy. But maintaining a complex, highly organized global tectonic system for billions of years without the cracks healing over? That is nearly impossible. Second stress test, initiating subduction is mechanically insane. For plate tectonics to be anything more than just a temporary crack, you desperately need subduction. You need old lithosphere to become heavy and dense enough to sink under its own weight. Now, oceanic lithosphere does cool down as it ages, moving away from the ridge. And cooling makes it denser and thicker. That helps gravity pull it down. But here is the catch. Cooling also makes the rock incredibly strong. And a strong, thick, rigid plate aggressively resists bending. It resists fracturing. It completely refuses to be forced down into the mantle like a stiff, unbreakable wooden plank. So subduction represents a massive physical paradox. You need the lithosphere to be old enough to be extremely heavy, but you need it to not be so strong that it refuses to bend and yield. What incredibly rare mechanism tips that balance? Third stress test, Earth's miraculous Goldilocks strength. If a planet's lithosphere is too strong, absolutely nothing breaks. You get no plate boundaries. You get no subduction. You get a dead, stagnant lid planet. But if the lithosphere is too weak, it can't form coherent, rigid plates. Instead of massive slabs sliding smoothly over the mantle, you get a squishy, distributed deformation. Imagine a soft, rotting piece of fruit that just wrinkles everywhere all at once when you squeeze it. No clear boundaries, no organized global recycling. Just a mushy mess. Earth somehow sits in a razor-thin, magical window. Its crust is strong enough to behave like giant rigid plates, but miraculously weak enough to fail completely at the edges. Why? How is this possible? Temperature absolutely matters. Chemical composition matters. The physical size of the planet matters. The sheer amount of internal radioactive heat matters. But there is one absolute prime suspect that keeps returning to the scene of the crime. It is standing quietly in the corner of the laboratory, pretending it has nothing to do with this. Water. Now we are going to go fully planetary. Because the absolute fastest way to deeply understand Earth is to see what happens when you change just one major variable at a time. It is like running nature's most extreme experiments across the entire solar system. Experiment number 1, Venus. I want you to imagine approaching Venus through the blackness of space. From far away, it is incredibly beautiful. A bright, shining pearl, nearly identical to Earth in size and mass, wrapped in a thick, reflective cloud cover. But as your mind descends through those clouds, the romance violently burns off. The surface of Venus is hell. It is literally hot enough to melt lead. That intense surface heat softens the mechanical contrasts that make brittle plates behave the way ours do. The atmosphere is an impossibly thick, crushing blanket of carbon dioxide, trapping heat and a runaway greenhouse effect. The pressure on the surface is equivalent to being a mile underwater on Earth. It would crush a nuclear submarine. And when we use radar to map the surface of Venus, what do we see? We do not see a clean, organized global network of subduction trenches and mid-ocean ridges. We see a surface that looks, in many vast areas, comparatively unbroken. It looks like a single, massive, stagnant shell. But Venus is not completely dead. It bears the violent scars of volcanism and heavy deformation. And here is the eerie, terrifying clue that scientists have pieced together. Venus may undergo a process called catastrophic resurfacing. Instead of the steady, calm, distributed plate recycling that we have on Earth, Venus traps its internal heat like a pressure cooker. It vents its heat in massive, terrifying pulses. It experiences hundreds of millions of years of complete lid-like stability, pressure building and building in the mantle, until the entire crust essentially fails and massive fractions of the planet's surface are repaved in oceans of magma relatively quickly. A violent, planetary overturn. Why would that happen? Why can't it just crack into plates? One major line of physical reasoning goes exactly like this: Venus is bone dry compared to Earth. It has no oceans. And here is the crucial fact: dry rock is massively stronger than wet rock. Dry faults are locked tight. Without water to chemically weaken the minerals and lubricate the points of failure, the thick Venusian lithosphere simply resists breaking into plates. Add to that the extreme surface temperature, which reduces the strength difference between cold and hot rock, changing how mechanical stresses concentrate. Add crust that might be too buoyant to sink. Subduction on Venus becomes an impossible trick instead of a sustained, billion-year habit. So Venus might have a fully convecting mantle, but it completely fails to translate that churning convection into persistent subduction. Experiment number 2: Mars. Mars feels like a very different kind of silence. Picture an endless, freezing, rust-colored desert under a thin, pale, unbreathable sky. And then, as you pan the camera, you see it. Olympus Mons. Olympus Mons is a volcano so incomprehensibly massive it is roughly the size of the entire state of Arizona, and 3 times the height of Mount Everest. It looks like the planet attempted to grow a mountain and simply forgot when to stop. Mars has giant volcanoes and enormous tectonic features like Valles Marineris, a canyon so massive it would stretch entirely across the United States. So, Mars clearly has internal activity. But it absolutely does not have Earth-like global plate tectonics. The likely reason? Pure physics. Size. Mars is significantly smaller than Earth. And in planetary physics, smaller worlds lose their internal heat much faster. Think of a small glowing ember pulled from a fire. It cools and turns gray long before the giant log does. Early in its violent history, Mars may have been much more active. But as it rapidly cooled, a massive, unimaginably thick and strong lithosphere formed. Convection deep inside became completely ineffective at breaking this incredibly thick lid. Global recycling simply stalled out and died. But volcanism could still persist in highly localized hotspots. Magma plumes rising from the deep mantle. Because the thick surface of Mars doesn't slide around on plates, that hotspot just sits exactly underneath the same piece of crust for hundreds of millions of years, violently pumping magma into the exact same spot, building one colossal, impossible edifice. So, on Earth, a hotspot builds a chain of islands, like Hawaii, because the plate is constantly sliding over the blowtorch. On Mars, the plate never moves. So the blowtorch just builds Olympus Mons. Experiment number 3: Mercury. Mercury is the stripped-down, brutally abused world. It is incredibly close to the Sun, heavily battered by craters, and unusually dense. When we look closely at its scorched surface, we don't see tectonic plates pulling apart. We see massive signs of planetary contraction. We see things called wrinkle ridges. These are huge compressional features that heavily suggest the entire planet actually cooled off and physically shrank, squeezing and wrinkling its own skin like a dried, aging apple. That is not plate tectonics. That is a dying planet tightening its belt. Rapid cooling and contraction entirely dominate its tectonic style. The lithosphere is incredibly thick. The convective driver is utterly weak. A global network of moving plates never even had a chance to take hold. And then, we have the wild, chaotic contrast case, Io. Io is a moon orbiting the massive gas giant Jupiter. And it is locked in a terrifying gravitational tug-of-war that physically kneads the moon like a ball of hot pizza dough. This process is called tidal heating. The intense mechanical flexing creates so much internal friction that it turns into massive thermal energy. This makes Io the single most violently volcanically active body in the entire solar system. Now, think about this. If pure internal heat was the only thing required to guarantee plate tectonics, Io should be an absolute paradise of beautifully moving plates. But it isn't. Io's surface is completely chaotic. It is constantly repaved by explosive volcanism and massive burial. It is not organized into elegant, Earth-like rigid plates with subduction trenches and ridge systems. So, massive heat is necessary. But it is absolutely not sufficient. We have now watched 4 different worlds answer our question in 4 completely different physical dialects. And the pattern is violently emerging. Plate tectonics isn't just having a hot interior. Plate tectonics is an incredibly delicate mechanical outcome. It is a rare, emergent planetary behavior that strictly requires the perfect conditions to translate blind convection into a broken, organized, mobile lid. So, what is Earth's ultimate hidden advantage? Here is the moment where this massive cosmic story tightens into something almost uncomfortably personal. You are back in the lab. You are watching a highly detailed cross-section of a subduction zone on a computer screen. A massive, cold slab of oceanic lithosphere is bending downward into the mantle. Deep earthquakes are ticking along the descending plane like falling dominoes. Each sudden snap is a tiny, violent declaration that the rock is still cold and brittle enough to physically break as it sinks into the fire. Above it, massive volcanoes line the surface, creating a luminous, deadly chain. And then you notice the subtle blue chemical signatures in the complex mineral diagrams. Hydrous minerals. Water-bearing phases. That sinking slab isn't just dry, dead rock. It is rock utterly packed with stored water locked directly into its microscopic crystal structure. Water is not just sitting out there on the surface of our planet making pretty oceans. Water is actually inside the machine. Now, we need to be extremely precise about what that physically means. Because saying, water lubricates the plates, is a nice, poetic spirit, but it is incredibly sloppy in its scientific detail. Water chemically and mechanically affects the rocks of our planet in at least 4 distinct, crucial ways. First, water dramatically weakens minerals. In many crustal and mantle minerals, the mere presence of hydrogen and oxygen from water radically lowers the physical strength of the rock. This means the rock can deform, flow, and bend at much lower stress levels. Imagine trying to violently bend a thick, completely dry wooden stick over your knee. It is impossible. Now imagine that same stick has been soaking in a bucket of water for a week. It yields. It bends. It's not that the wet would turn to liquid, it's that the internal molecular bonds are willing to yield far more readily. Second, water fundamentally changes the friction on gigantic faults. Faults are not smooth, clean planes of glass. They are terrifyingly jagged, rough contacts trapped under millions of tons of pressure. Water alters the chemistry at the tiny grain boundaries. It influences intense pore pressures inside the rock, and it physically changes how massive faults slip. It literally makes some forms of catastrophic failure easier to initiate. Third, water enables melting. Deep in the mantle, injecting water dramatically lowers the melting temperature of the surrounding rock. It works exactly like throwing salt on an icy sidewalk to change its freezing behavior, just in reverse. Hydrated mantle rock sitting directly above a subducting slab can melt far more readily. This massive influx of melt feeds the explosive arc volcanism at the surface. And that volcanism is not just a pretty fireworks show, it is a critical part of how billions of tons of material and massive amounts of heat move through the planetary system. Fourth, water alters density and phase behavior. As the heavy slab descends deeper, the extreme pressure causes the minerals to transform. Some of these dramatic transformations squeeze the water out, releasing it violently into the surrounding hot mantle wedge. That water doesn't simply float away. It participates in wild chemical reactions that further weaken and profoundly modify the entire tectonic system. In other words, water is a powerful rheological catalyst. Rheology is the deep physics of how solid materials flow and deform. Think of rheology as the hidden personality of rock when you put it under unimaginable stress. Water can magically make that rigid personality far more willing to bend, to slip, and to fail in exactly the right places to keep the machine running. And suddenly, looking at this data, Earth's vast blue oceans look like so much more than just pretty scenery for whales and ships. They look like the literal master control knob on planetary mechanics. Now, the final, terrifying thought experiment becomes absolutely unavoidable. I want you to imagine an Earth with the exact same mass, the exact same crushing internal heat, the exact same radioactive inventory of uranium and thorium, the exact same starting chemical ingredients, except for one thing. No oceans. A completely dry surface. A bone-dry mantle. Dry locked faults. Dry, ultra-strong minerals. Would the very first subduction zone ever manage to catch and keep running? Or would every single agonizing attempt to bend and break the thick lithosphere stall out, snap back by the sheer, unyielding strength of dry rock until the entire planet gave up, completely locked up, and settled into a terrifying stagnant lid exactly like Venus? You can physically feel why this specific question matters so deeply. Because it means that plate tectonics might not be some inevitable destiny for a rocky planet. It might be wildly contingent. It might be incredibly, impossibly rare. Now, we must be careful here. Science is not a dramatic courtroom where we convict nature based on pure vibes. Venus's tragic lack of plate tectonics likely involves a massive, complex web of interacting factors. Insane surface temperatures, a lack of water, highly buoyant crust, mantle viscosity, the exact way heat escapes, the planet's early geological history, perhaps even violent, massive asteroid impacts early in its life that forever set its boundary conditions. Mars's dead story involves rapid cooling and tiny size. Mercury's dead story involves violent contraction. Io's chaotic story involves insane tidal heating and bizarre resurfacing modes. But if we are auditing the absolute best current scientific synthesis, what the math and the physics actually point to across all our models and all our planetary observations, the through line is blindingly clear. Turning churning convection into the elegant machine of plate tectonics strictly requires a lithosphere that can both form highly coherent, rigid plates and successfully, repeatedly fail at their boundaries. And water appears to be the magical key that helps make that continuous failure achievable and completely self-sustaining. So, the mystery profoundly transforms. At the very beginning of this audit, the simple question was, do continents move? Now, the terrifying question is, why can Earth magically keep doing this for over 3 billion years? Why can it maintain this perfect, balanced loop of violent creation and violent destruction, while every other world we look at, even our closest siblings, completely fails to do so? And at this exact point, the implications of what we are discussing spill violently out beyond simple geology. Plate tectonics is not just a boring study of rocks. It is a planetary operating system that keeps you alive. It continuously recycles massive amounts of carbon between the surface and the deep interior. Carbon dioxide dissolves in falling rainwater. It weathers the rocks. It gets carried by rivers into the ocean. It gets buried in deep-sea sediments. And through the violent magic of subduction, it is dragged deep into the mantle, only to be eventually released again millions of years later through volcanic eruptions. Why does that cycle matter to you? Because atmospheric carbon dioxide is not merely a modern industrial pollutant. On a geological scale, it is the planet's primary thermostat. If you have too little greenhouse effect, the oceans freeze solid, and Earth becomes an ice ball. If you have too much, the oceans boil, and Earth becomes a hell's cape exactly like Venus. Over vast spans of geologic time, the machine of plate tectonics physically helps regulate our climate by perfectly coupling the atmosphere, the oceans, and the deep crust in a massive, slow, highly imperfect, but beautifully stabilizing feedback loop. Plate tectonics physically builds the continents. Thick, buoyant platforms of lighter rock that grow larger through violent collisions, arc magmatism, and constant recycling. Continents are not just boring landmasses for us to build cities on. They are massive chemical archives and dynamic nutrient factories that feed the oceans. Plate tectonics violently creates gradients. Extreme differences in temperature, chemistry, and pressure that biological life can exploit for energy. Think of the boiling hydrothermal vents sitting on the mid-ocean ridges. Volcanic island arcs. Massive mountain ranges that drive weather patterns and massive nutrient flows. A restless, violent Earth is the only thing that creates the dynamic niches required for evolution. So, when we casually ask why Earth has plate tectonics, we are quietly, desperately asking why Earth managed to stay habitable long enough for complex, intelligent life to actually emerge and look back at the stars. Now I want you to step completely outside the dry science for a breath. I want you to physically feel the human scale of this reality. The ground beneath your feet feels intensely permanent because your lifespan is incredibly, laughably short. You live inside a tiny, microsecond time window where towering mountains seem eternal and vast oceans seem perfectly fixed. But zoom your perspective out to the millions of years. Earth is a living, breathing calculation. It is continuously solving a massive thermodynamic heat problem by constantly, violently moving billions of tons of solid stone. There is a deeply unsettling, yet beautiful comfort in that realization. The exact same violent process that destroys human landscapes, the massive magnitude 9 earthquakes, the explosive volcanic eruptions, the terrifying subduction that brutally drags entire ancient seafloors down into the dark, is the exact same process that keeps this tiny blue dot habitable over the unfathomable abyss of geological time. Stability on planet Earth is not stasis. It is not freezing in place. Stability is highly managed, violent, continuous change. So here is our final audit statement, clean, precise, and completely unsentimental. Earth has drifting continents because it magically found a highly sustainable, mechanically perfect way to constantly break and recycle its own outer shell. It maintains a mobile lid driven by deep internal heat, perfectly organized into massive plates that are continuously born at mid-ocean ridges and violently destroyed at subduction zones. Most rocky planets simply do not do this. Not necessarily because they lack the internal heat, but because they completely lack the wildly narrow, magical mechanical and chemical conditions, especially hydration, that are required to turn that heat into persistent, global, subduction-driven motion. And if you really let that physical reality land in your brain, the solid Earth directly under your feet suddenly becomes incredibly strange. Your entire continent, your country, your home, it is not just where you live. It is a highly temporary arrangement of buoyant rock. It was brutally assembled by massive collisions. It was heavily modified by thousands of volcanoes. It is constantly being erased by rain. And it is ultimately destined, at least in some part, to be dragged down and recycled back into the fire. Now I want to leave you with a single thought that you can carry into tomorrow. Take the place you know best. Your neighborhood. Your favorite coastline. The massive mountain in the distance that you think of as utterly immovable. I want you to imagine a time-lapse camera that runs not for minutes, but for 200 million years. Watch the solid ocean floor rip open like a bleeding wound, and then watch it slowly close up like a perfectly healed scar. Watch your continent violently split in half, drift across the globe, collide with another landmass, fold up into towering, jagged mountains, and then slowly grind down to sand. Then ask yourself this: if the solid ground of reality is this terrifyingly dynamic, what else in your life feels absolutely permanent only because you simply haven't watched it for long enough? And then, the next massive, terrifying question opens up, almost completely by itself. If global plate tectonics deeply depends on the presence of water, if Earth's massive oceans are literally a required part of the internal machinery, what does that imply for the massive search for life on exoplanets? When we point a telescope at the dark and find a perfect, Earth-sized rocky world sitting right in a habitable zone, are we actually looking at a beautiful potential cradle for alien life? Or are we just looking at a familiar radius that is completely hiding a dead, stagnant, terrifying alien fate? If you want to keep going down this rabbit hole, I highly suggest you click the video on the screen right now. I built it specifically to pair with this exact audit, because it pushes this terrifying mystery into the next, much deeper layer. And if you want a massive reason to subscribe to this channel, here it is. Every single week, we take a scientific claim that sounds completely settled and boring, and we violently stress test it until the hidden, mind-blowing reality becomes visible and totally usable in your own daily thinking. I have one simple, genuine question for you before you leave. If you had to bet all your money on just one ultimate factor, water, internal temperature, planet size, or something totally different, what do you think is the single most important variable that decides whether a planet gets plate tectonics or dies as a stagnant lid? Leave your answer in a single sentence down below. I will be reading and replying to them.